Hello once again. We're coming to you from the sports stadium in the downtown core. Today's topic is the test of two proportions, and this is presentation 9.5. We're going to focus again on the notion of the variances add together, and the contents of this material contained in your textbook and workbook in chapter 9. We want to acknowledge the development team of Brad, Spencer, and Amanda. Now we're going to review the material from the video 9.1. We start with two populations. We call them X and Y, with mean 70, standard deviation 18, and for Y, mean of 80, standard deviation 20. Now these are populations. Under repeated samplings of 36 from population X, they'll be normally distributed with clustering around 70, and standard error given on the screen is 3.0. Similarly with the population Y, if we undertake repeated samplings of 25, we find the sample means will cluster around 80. Standard deviation Y would be 4. You see on the screen now. Now if we systematically take the difference between the Y bar and X bar, we have them coming on the screen here. If you take the differences, these differences will cluster around 10. The difference between mu Y minus mu X. The standard deviation, however, add together in the following sense: the standard deviation of x squared plus y squared, and the square root gives you the standard error in the distribution of differences, which in this case is 5.0, which is remarkable in the sense that the variations do add together, but only in the sense of Pythagoras' theorem. And we're saying that this is really follows the Pythagoras theorem, where two vectors are independent, much like our two populations, independent populations. The variances add together in the sense of Pythagoras. Now we're going to apply that to the case of a test involving a drug called Xylophon, used to treat arthritis and nausea. We have on the screen coming here sample 58 under placebo, 8 experienced nausea, 88, 18 under Xylophon experienced nausea. We want to check and see if there's any difference between these. And looking at the percentages here, 8 of 58, 13.8%, 20.5%. Now for reasons which you don't know yet, we add these totals together. 26 out of 146 together experienced nausea. That turns out to be 17.8%. We're going to use that throughout the initial part of this test that you'll see coming on the screen here. The hypothesis, null hypothesis, that Xylophon does not have a significantly higher rate of nausea than placebo. We're going to look at the idea that taking the differences here, under HA, the difference is greater than 0. So this is the one-tail test, looking at the distributions of proportions based on n equal 58. Now we're using our estimate p hat here, 13.8%, and that gives us a variability of 0.045 about the population proportion here. Similarly with the Xylophon, the standard error turns out to be 0.043, and that's the variability about the mean here. Now if we systematically look at the differences, assuming that the difference is 0, then the sample proportions, the differences will cluster around 0. Now the standard error, note on the screen here, we're saying if we assume the two proportions are the same, we should come up with some sort of an averaging process here, which is not quite the average. We look at the totals here, 17.8. Notice it's between these two percentages here, and use that in our calculations. That gives us a standard error, 0.0647, and that's in the differences, the distribution of differences. Now looking at the test criteria for 5% tail, critical value, we reject and fail to reject under the circumstances here. And bring on the evidence against the null hypothesis. Let's see what you've got. The observed difference, 20.5 minus 1.138. And note here, this comes out to be 1.0355 within that critical region, so we fail to reject H0. There's insufficient evidence here to reject H0. The p-value, looking this up in your table, is around 15%, which is not unusual based on what were true. Our conclusions would be insufficient evidence to reject H0. Now we're going to show you a confidence interval. It's the estimated difference plus or minus your margin of error. And here's your estimated difference. Here's your margin of error here, 1.96. Note here we revert back to our original proportions that you see at the top of the screen, because we no longer make any assumptions about the proportions being equal. And this turns out to be an estimate of the proportion of the difference, 5.5%, negative 5.5%, and 18.9. And notice 0 is in this interval. Therefore, we can't reject a two-tailed null hypothesis of the two being equal. And that's the end of presentation 9.5. We ask you to take notes as required and go to presentation 9.6.